Hello guys, welcome to the Data Structures and Algorithm course brought to you by Asha Akanksha Foundation. So in this lecture we will talk about the time complexity and in general big O notation. So let's start with the lecture. Now in the time complexity we first need to compare the efficiency of algorithms. Okay. So how do we compare the efficiency of two algorithms? Let's take a look by mm, looking at this algorithm which has time complexity 2n square plus 125. Alright. And the other algorithm has time complexity 5n square plus 67n plus 400. Don't take it as a time complexity, but for now take it as an equation only. Now the question is which algorithm is more efficient in your perspective. So you can take a look and obviously say that for a value of n algorithm equation B has for algorithm equation A gives us much more lower value than the algorithm B. So it means it takes less time than the algorithm B because it is giving us less value for high values of n. So from that, this is a very vague idea. I'm not saying that we need to calculate by we need to calculate time complexity by putting values of n. I'm just building upon this idea, and at the last we will be able to efficiently calculate the time complexity of an algorithm. So now mm, we will further go on the basic idea of comparing efficiency of two algorithms. So taking the example which we discussed earlier, we will now change the algorithm B, and the algorithm B we can say that it can be 50n plus 125 for now. So this is but if we apply the same method we applied over here, that by putting values of n we check which of the algorithm is giving us less value, and we said that that algorithm is more efficient. If we apply the same method over here, we can find that A is more efficient than B for n less than 25, but not in the case when n is greater than 25, because B will give us less value than A in the case when n is greater than 25. So calculating time complexity from this method is a issue when the input size is quite large. So we will discuss some more criteria for time complexity, but for now just we should assume one rule that we compare the time complexity for high input values only, or you can say asymptotically large value, which tends asymptotically basically which tends to infinite when the input size is very high. So now we will compare two algorithms. We are given algorithm B as 50n plus 125 and algorithm A as 2n square plus 125. So as we know that for n greater than 25, we discussed over here that for n greater than 25, B is more efficient than A. So we can say that asymptotically algorithm B is more efficient than A. Asymptotically means for very high value of input, or for very high value of n. So for a very high value of n, algorithm B is more efficient. So let's take a look at a few other algorithms also. Let's say algorithm A has time complexity 5n square plus n plus this 1250, and we also have two more algorithms which has these equation for the time complexities. So the question is which of the algorithm in B and C is more time efficient than A in the true sense. So how can you calculate that? As we know that uh, time complexity is calculated for asymptotic values, like for very high values. So we can apply the limits and derivatives which we had learned in 10th class to this question, and we can do asymptotic analysis of these equations. So we can divide these two equations, like if we are comparing algorithm B and algorithm A, we can do asymptotic analysis over here, and by doing this we get 1 by 5, and by doing the algorithm C asymptotic analysis with algorithm A we get 0. uh, so 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 if we combine all the idea that discussed in the above slides, we come up with a rule too, that an algorithm X is superior to another algorithm Y the ratio of the time complexity approaches zero for very high values of n, or we can say for asymptotically large input size. So you should be familiar with this rule too, and it should be fingertips for the time complexity algorithms. So now we would we would observe some observations which we had seen in the previous slides. So for these algorithms, algorithm A, B, and C, if we want to compare these algorithms, we will take the asymptotic ratio of these algorithms with each other, and we will come up with the idea that algorithm C is the most efficient of all. We can rather take a look on these algorithms, and also we can also conclude that algorithm C is most efficient, as you can see that A and B are quadratic equations, but the degree of the degree of equation algorithm C is not 2 but less than 2, which is 1.5. So we can also so by just looking at this, we can also say that algorithm C is most efficient. So looking at this, you should also be come up with other observation that multiplication of addition of constant do not generally make a difference in time complexity because it is asymptotic analysis, and it doesn't make any difference in their equation. And as we have discussed, the degree of the polynomial, or we can say the highest order term, governs the time complexity asymptotically. This is the major thing you want to remember for calculating time complexity. Now let's take an example of time complexity of a matrix multiplication. I guess you know how to multiply a matrix. If you don't know, just check it out on Geeks for Geeks. I'm not saying that you should be able to solve it, but just take a look. We are now just discussing for the time complexity reason only. We will see how we will calculate that in the later video. So in the matrix multiplication, we have two for loops. One for loop is from 0 to n minus 1, or we can say one for loop is for the x-axis and one for loop is for the y-axis. So in both the for loops, we are traversing n times. So and in the last for loop, we have just constant works, or we can say n plus 1 instructions. And but in the last for loop, we have one another for loop which is also traversing uh, n times. So here the time complexity, as you can see that there are three for loops, the time complexity will be order of n cube. But if we calculate the equation, it comes out something like this: n cube plus n square plus 1, because there are um, two traversal of n times over here, and one, and if we sum up all these instruction, it would be n plus 1. So if we multiply all these, we can get these equation. So let's go ahead and talk about what is order notation. Order notation is a mathematical way to capture the intuitions developed till now. What we have uh, seen in the previous slides, that we are trying to calculate the approximate time complexity of an algorithm for asymptotic high values, and that is what order notation is. So this is a very mathematical definition of order notation. I don't recommend you to learn through this definition, but learn it intuitively. So I will not uh, focus much on this mathematical definition. I will skip this slide. So we will look at the order notation with the help of some examples. Like if we are given 20n square, as we have seen the observation that a multiplication of any constant or addition of any constant doesn't make any difference on or time complexity, because it is an asymptotic analysis. So uh, we say that the time complexity of this algorithm, that is 20n square, is order of n square, because the n square is the highest order term over here. And 100n plus, we can also say that time complexity of 100n plus 60 is equals to order of n square, but this is a very loose approximation, and we tend to tend to get the tight approximation. So rather than say that 100n plus 60 is order of n square, we will say that 100n plus 60 order of n, because it satisfies this and these both, but much tighter approximation is order of 10. So the same ideas goes through these two examples only also. So from the examples we come up to a two simple observation that you can see over here. This is a very mathematical observation. So you can take a look over here. So now we will uh, just take a look which we had on the intuition which we had developed till now. So this is algorithm P. This has time complexity as n square plus 10. So we can obviously say that the order notation of this is n square. Now other algorithm C, which has time complexity 10 n to the power 10 into n to the power 1.5 plus 10, 20 into n plus 2000. So since n to the power of 1.5 is the highest order term, we can say that time complexity or asymptotic time complexity is order of n to the power of 1.5. So if we have one n cross n matrix, we have seen that the time complexity equation comes out to be n cube plus n square plus 1. And so the order notation would be n cube, since n cube is the most highest order term. So the efficiency just not depends on time only, it also depends on space. So whenever we analyze an algorithm, it means that we are developing a formula for predicting how fast an algorithm is based depending on the size of the input. In the time complexity, we take it asymptotically, or for very large input size. And similarly, we develop a formula for predicting how much memory an algorithm requires depending on the size of the input. But in general, the time complexity is our biggest concern, and most algorithms doesn't require that much amount of space. So, so now we'll discuss what is the size of the input. So let's take an example where we are searching for an array, and searching in an array, the size of the input will be the size of the array. If we are merging two arrays, the size will be the sum of the two array sizes. If we are computing the Fibonacci number, the factorial which is equal to nth factorial, the size would be n. So now we'll discuss what is constant time complexity. Constant time complexity just means that there is only some constant amount of operation, let's say k, which takes so a time complex so an algorithm which just take some k constant amount of operations is known as constant time complexity. For example, if um, uh, if an algorithm does not include a loop, or an algorithm which does not include calling a function which has a linear or more than a time complexity, you can say that that algorithm is constant time complexity. Or if a statement involves a choice like if or switch among operation, each of both takes constant time, we will consider that statement to take constant time. So this is for big O. It is the most common method and notation for discussing, or you can say expressing, the execution time of algorithm. The operation which have constant time complexity is represented by order of 1. For dictionary, the algorithms requires order of log n steps to search for an item. For an unsorted list, the linear search algorithm requires order of n steps. Big O is the expression of asymptotic execution time of the algorithm. So let's take a loop that work on a dataset. This is the loop which gives us the minimum value in the array. So number of executions of the loop here, which is for finding the minimum, depends on the number of elements in the array. So we can confidently say that the runtime, or you can say the time complexity, is order of n, because we are iterating over all the elements in the array. This is let's take another example of linear search. In linear search also, we were searching for an element in the whole array. So here also the time complexity would be order of n. So we can, I guess, till now you are you can confidently say that constant time is better than linear time. Uh, if you are not, so we will not take an example to make this concept clear. Suppose we have two algorithms to solve a task. Algorithm A takes 5000 time units, and algorithm B takes 100 multiplied by n time units, which is also, you can also say that it is a linear time complexity. So I will ask you a question, which is better in both of these algorithms? So clearly algorithm B is better if our problem size is small, or you can say n is less than 50. But since the time complexity is a measure of asymptotically higher values of input, in that perspective algorithm A is better for larger values of n. Um, uh, so 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 we can say that algorithm A takes much less time than algorithm B for high values of input. And in the time complexity, we usually just care about asymptotically high values of input. So we have discussed about loop, uh, but the modification, or you can say in the loop we also have nested loops, which is two or three loops in which is multiple for loops in single for loop. So as you can see that we have also discussed a matrix multiplication example, which is similar to this, which is also a nested loop. Here there are two for loops inside each other. So this for loop is traversing n items, as we can see, and this for loop is traversing from j is equals to 0 to I. So I will ask you a question over here that you have to calculate the number of execution which is done in this for loop. So pause the video and try to give the answer. Now, till now, you might got a question in your mind. We are justifying. Can we justify Biko notation? Because we are just talking about the asymptotic values of input in the Biko notation, uh, or it is defined only for a very large problem size. So does it? So to clarify this question, we'll take an example like consider r is equals to x square plus 3x plus 5. So we can say that for different values of n, we have different values of r. So over here you can see that Pico notation does justify, or you can say usually simplifies the time complexity or time efficiency algorithms, and it gives the idea of how much efficient a time an algorithm is. Some examples of BIGO is like these. Three BIGO notation of 3n cube is n cube, and you can take a look at this, and you can also solve this if you want by pausing this video. Let's try to plot this equation on a graph. Y is equals to x squared plus 3x plus 1. So while plotting this graph, you should get something like this. So what can you infer from this graph? If you have any answer, you can pause the video and try to think of uh, answer you come up with. So from this graph, you can say that fn is this x square plus 3x plus 5 is the actual growth rate of algorithm, and gn is the function from this red line which bounds that growth. There can be two bounds, upper bound or lower bound. So lower bound is the function this 3x, or you can say seek from the orange line, which constrain the function to go beyond this. These upper bounds or lower bounds may not be equal to the function f of n, but it guides the function to remain in this region. See, these are some of the common time complexity which we generally use. constant time, log of time, which we use in merge, in sorting and binary search. This is linear time. Then we have n log n, n square, n cube, 10n. So from the top to the bottom, we from the top to the bottom we have sequentially written this algorithm which has more time complexity, or you can say which has worse time complexity. Order of 1 is the best and order of 2 to the power n is the worst time complexity. So these are some common algorithms with the time complexity given inside. Like for the n factorial, we have time complexity is n factorial. For exponential function, we have time complexity of 2 to the power of n. Polynomial, we have the highest degree as the time complexity. Highest order term is the time complexity. And for the cubic quadratic, you can calculate using this polynomial formula only. So in this example, we will see how this time complexity has a great impact on the execution of an algorithm. We have given some functions and their running time. These functions are these functions are described with the time complexities or even big O notations. So for two, if we have n is equals to 1000, input size is quite large, and the speed of the processor is 1 lakh operations per second. If we calculate this, 1 lakh operations per second is a very general speed. It is not the most optimized and not the highest, but in general we have this in computers. So if we calculate the runtime with of these algorithms, we'll get that runtime of 2 to the power of n algorithms is over 100 years. So that means that you cannot even see to end to see the end of this algorithm. For n cube, it is 31.7 years. So I will give you a very good example of how much a great impact can a linear algorithm have from a quadratic algorithm, which is n square. So you can see the runtime of a quadratic algorithm or order of n square algorithm is 2.8 hours. But if the algorithm becomes a linear time complexity algorithm, the runtime just changes to 0.1 second, which is which is the 1000th part of the runtime of or quadratic time algorithm. So this is how this is how time efficiency plays a role in real life, and it has a great impact on the processors and the runtime of an algorithm. So this is it for this lecture. We will talk in the next video we will talk about the recurrence relations. Recurrence relations is calculating time complexity for complex equations and for the recursion problems also. So if you have any questions, you can comment down below, or if you have any query, you can also reach us to us at our Insta and Facebook pages. So till now, stay safe. Hope to see you in the next lecture. Thank you.